24:30. So 5.
All right, hello. All right, so where we left off last time, we had been talking about kind of the remaining stuff in our solar system: asteroids, comets, meteors, meteor showers, and the last thing that we didn't get to in last lecture was a section just on impacts, right? Like the possibility that these meteors can actually cause destruction, right? Before we get to the lecture material, are there questions? All right, so we've actually seen examples of impacts of other planets. Here's one, a famous one of a comet where tidal forces from Jupiter. Remember, we talked about in the last lecture, we talked about Roche limits and how if something is kind of loosely held together just by gravity, if you get too close to a large planet like Jupiter, you'll actually begin to rip it apart. Okay, so like for example, the Roche limit for Saturn is a little larger than its rings, and that makes sense because something closer to Saturn than its rings can get broken apart, and that actually might be the origin of Saturn's rings. So here we're watching a comet arrive at Jupiter, and it got broken up into many pieces. And we watched as those pieces impacted Jupiter, okay, leaving kind of splashes in the atmosphere that you could see for days. And we actually see examples of crater impacts on, for example, here's Ganymede, but we see this on the moon as well. Places where we see lots of craters, sometimes we see these strings of craters in a line, just to see this. So this is called a crater chain. We see a string of craters. What would create a string of craters all in a straight line? Well, it would be one object, like a loosely held collection of debris in an asteroid or a comet that got too close and got pulled apart by the tidal forces. And then so you have kind of a string of debris, all that arrive at slightly different times, forming like a shotgun pattern. Like a machine gun line pattern. Okay, here's an example on Callisto. And by the way, this, you see this a lot on Ganymede and Callisto or other moons of Jupiter that don't have a lot of tectonic activity, right? So they're not tectonic, volcanic activity that would erode the craters. You can actually see them because they are moons of Jupiter, and Jupiter has really strong tidal forces. On Earth, there are countless, pretty much we count them, but almost innumerable numbers of small asteroids are constantly disintegrating in Earth's atmosphere. Here, over a 15 or so year period, 1994 to 2003, here's just an example map showing small asteroids that disintegrate. They kind of blow up, they leave a streak in the sky. If it's nighttime, you see them. And we call those bolide events. That is, events that don't leave a meteor on the ground or a crater. They just cause a streak in the sky and disintegrate in Earth's atmosphere. And we can count them, right? We have observatories that look for them. And you see that they're just as, even though you only see meteors at night, right? They're just as common during the day as during the night. So here in blue are showing the ones at night, and yellow are showing the ones during the day. The other thing you see from a map like this is that they're pretty much equally distributed, right? You're just as likely to get a meteor come from one direction as from any other direction. Okay. Remember, of course, part of that is because the Earth is rotating. So even if we do, every year come through the same, say, meteor shower from old cometary debris, right? The Earth is rotating, so a different side of the Earth might be near that debris at that time of year. And you see different sizes here. Here we're measuring them in gigajoules, billions of joules. So that's a unit of energy. But you can also have of course, meteors that leave craters. And we've identified over 150, some of them small, like people's, this in someone's backyard or farm, right? Just a small one right here in Peru. Two really, really large ones that happened millions of years ago that we can only see kind of the broad outlines of the craters, because remember, Earth has volcanic activity, plate tectonics, so we tend to, and we also have weather and erosions. We tend to remove and resurface the Earth, making craters that are old hard to see. Remember, that's why, when we look at the moon, it's heavily cratered, but the Earth isn't. That's mostly just because we've had just as many craters. It's just they've been eroded over time and smoothed over due to volcanism and plate tectonics. The most recent, really, really large meteor that struck the Earth was most likely, we don't have, this was a time before we had dash cam footage on people's cars, but most likely was this 1908 Tunguska event, where in Siberia, people heard a huge boom. This was more or less in the middle of nowhere, but here's a photo, enormous number of trees flattened over a very huge area. And what this likely was a very, very large bolide, that is a very, very large meteor that blew up in the atmosphere. And instead of leaving like a crater, it left, just devastation. So that was here in Siberia in 1908. So it's the most recent, really major one. That if it happened today, it would have devastated a city, would have destroyed the city. Another cool thing, though, is in the modern age, right? A lot of people have dash cams, especially not as common in the United States, very common in places like Russia. Here was a very large Russian a meteor in 2013 that was caught on dash cams. You can see that you Google it, look it up on YouTube, you'll see the dash cam footage of this. This blew out, shattered glass windows, and people then were able to hunt and find bits and pieces of the meteorite that came from this large explosion as it entered and kind of broke apart in the Earth's atmosphere. So even though we talked about meteor showers that are very common and have happened multiple times a year, they're due to little pea-sized asteroids or cometary debris. In our lifetimes, we can expect to see pretty large meteors, ones like this that may be a meter or more in size, striking the Earth. The most recent, kind of really big crater that hasn't yet been eroded over time or, recovered through resurfacing of the Earth is this, sometimes called meteor crater in Winslow, Arizona. So you can go visit it. It's beautiful. I visited it. As you can see, it just looks like a massive crater, just the sort of crater you'd see on the moon. That's because it's only tens of thousands of years old, right? It hasn't eroded to nothing yet. Over millions of years, it will be kind of covered in dirt and eroded, and it'll be hard to see. But so we see that in terms of tens of thousands of years, we can expect really big meteor impacts hit the Earth. Whereas in our lifetimes, 100 years ago, we got the Tunguska event. So maybe over the course of 100 years, we can expect pretty major meteors that could strike a city and cause some devastation, although most of the Earth is ocean and forest, so hopefully it wouldn't strike a city. And then over tens of thousands of years, we can expect things like this, things that could be even more devastating if they struck near a population center. Now remember, there were more meteor impacts further back in time. One of the really large ones that we can see some evidence of about 2 billion years ago is called the Vredefort Dome. So you wouldn't notice this unless you had a satellite. You take satellite pictures and you see something like this that seems to be evidence of a huge, more than 300 kilometer sized impact crater from 2 billion years ago. Right, and so this is something we worry about, and it's something associated, you probably heard, with the extinction of the dinosaurs about 60 million years ago. So we think that some mass extinctions in Earth's history have come from meteor impacts. I'm on a stool here, so I almost fell over. So we have fossil records, right? So we can see that there are occasional mass extinctions, sometimes just suddenly the diversity of life on Earth suddenly changes very drastically. And the most recent one was 66 million years ago, where suddenly the dinosaurs ceased to exist. Okay, and so what we can do is we can look back in the fossil record, and you see all the dinosaur bones, and then suddenly there's this line where it looks like there's lots of ash, something catastrophic happened. And there's also a lot of iridium. So this is what I have in my third bullet point. A very rare element that's found in asteroids, but not very much on Earth. So you have a layer with iridium, and then suddenly there's no dinosaur bones anymore. Okay, life on Earth changed like in the blink of an eye in terms of geologic history 66 million years ago. And it turns out that anywhere you looked on Earth in the geologic layers of rock, there's this line. Okay, this boundary layer that has a lot of iridium, below which there's dinosaur bones, and above which there isn't. So we think that probably there was a catastrophic meteor impact 66 million years ago that killed a huge amount of variety of life on Earth. And there's an artist's conception of what it may look like. It would have caused massive flooding and kind of hot burning ash to kind of burn down forests, and in a matter of days could have destroyed a huge amount of life. And then after that, it put a huge amount of ash in the air and would have changed the temperature, causing then over decades after that even more reasons why life might suddenly die. So we call this the KT or KP extinction event. And that is Cretaceous Paleogene, right? It's the line between those two periods, dividing line, where about 3/4 of all plant and animal species died. Like I said, there's the thin layer of sediment spread all over the Earth corresponding to this event. It's also filled with little evidence that of like melted rock, basically ash. And there's a crater that we think is associated with this event called the Chicxulub. I'm not sure if I'm pronouncing that right. Crater in the Yucatan. Okay, and there's also evidence of giant tsunami beds. In other words, there were giant floods around this time, 66 million years ago. Here's a photograph of it, and you see this all across the Earth. This particular line. And again, below which there's dinosaur fossils, and above which there are none. Okay. Here in the Yucatan Peninsula, we think is this evidence, and again, you can't see it except if you map the ocean floor, you can see evidence of a very large crater. And so we suspect that this is probably the location of this, or the location of this catastrophic meteor impact. Causing kind of a winter for at least 10 years, which could be additionally devastating for life on like the other side of the planet, even if it wasn't directly affected by the meteor impact. Okay, so it could have been climate change in addition to the direct damage caused by the meteor that caused. Now, there are countless bits of debris in our solar system. I showed you there's dust, there are okay, and once we get to like a kilometer in size, we're talking creating widespread devastation. Okay, and maybe something needed for mass extinction, something maybe 10 kilometers size, like the dinosaurs, maybe that only happens every 100 million years or so. Okay, so this is something we have to be aware of, that it, it could happen that in our lifetimes, now on average, in a human lifetime, about 100 years, on average, you'll get maybe a 10-meter size asteroid hitting. And that would maybe leave a small crater that could create a really large atmospheric explosion, but probably not going to hurt us. Okay, so it's unlikely in our lifetimes that we'll see a devastating one, but it's possible. Every 1,000 years, so every 10 human lifetimes, you're approaching where you start to cause some devastation from an asteroid. So this is something to keep in mind, and it's why we track all sorts of near-Earth asteroids, because if we see one with a long enough, if we track one and we see that in 100 years it'll hit us, then maybe there's something we can do about it. Then maybe we can send up a mission to give it a little nudge so that in 100 years it'll miss us. But we need a lot of lead time. Okay, so yeah, we call these potentially hazardous objects, that is near-Earth objects large enough to create significant damage, and we track them. Not enough money is put into this, so it's a tiny, tiny, minuscule fraction of like even NASA's budget, unfortunately. I think we should be putting more money into it because it could potentially save our lives. With that said, I'm ready to shift gears to the next topic and the next lecture material. But are there any questions at all about asteroid impacts? All right, if not, then we can talk for the rest of today about other solar systems. In particular, we're talking about what we call exoplanets. That is the fact that we're beginning to have the ability, this is new, this is only in the last 20 years or so, we're beginning to have the ability to observe solar systems outside our own, including planets around other stars that we call exoplanets. Okay. So what we have learned over the last couple decades is that exoplanets are common. Okay, exoplanet is a planet that orbits a star outside our solar system. And I'll talk about the ways we detect these planets in a moment. But one of the main methods, gravitational microlensing. So just that on average in our own galaxy, most stars host at least one planet. Okay, so our solar system is not unique. Most stars have at least one planet orbiting them around them in the range near where Earth orbits our own sun. Okay, about 1 in 5 stars that we've looked at, so about 20% of all stars in the Milky Way have a planet that's like Earth-sized, in what we call the habitable zone. That is close, not too far from the sun, not too close to the sun, such that it could support liquid water and potentially have life on. So I haven't updated this in a couple years, but we keep discovering more and more exoplanets. Okay, so as of a couple years ago, we had confirmed about 4,000 exoplanets. Maybe the number is 5,000 now. 700 solar systems with more than one planet, and we keep discovering more planets. So this isn't definitive. We might, just as in our own solar system, we're still discovering more objects. We may in the future change these numbers, right? And say, oh, now there's 800 multi-planet systems. Maybe there's 1,000. So these are just what we've found. And so NASA maintains this large archive of all of these exoplanets that any one of you or myself can look at and view the data. And I'll show you some plots today from it. So here's just showing, for example, like how many exoplanets have been discovered with different sizes. So, for example, there's been 400 or so that are about Earth-sized. There are about 100 or so whose radius is more than 15 times the radius of the Earth, and also by mass. So we've discovered about 39 that are less than 3 times the mass of the Earth, all the way up to like 380 that are more than 300 times the mass of the Earth. Okay, and so I have a link here. You can go to their archive and plot some of the plots that I'm going to show you today. Here's an Onion article: New planet discovered 400 light years away from public's interest. So, of course, this is something that it's something that the public is generally more interested about in some things because of the potential for alien life. But this is something that's really exciting for us. Again, this is something that we've only been doing for the last couple decades. We are literally able now to discover planets orbiting other stars that may potentially harbor life and may have the conditions for life. One thing to understand is all these numbers I'm showing you, that we've discovered, a few thousand exoplanets. This is all in this tiny region of our galaxy that's close to us. Okay, that's because it's hard to see, right? It's hard to see things that are far away. And so our neighborhood kind of around our own solar system where we're looking for planets is all in this tiny little bubble I've shown you. About with everything, we're looking out to about 2,000 light years away from us. All right, how do we detect these exoplanets? Well, here's a quote from one of the main telescopes that search for exoplanets, their collaboration. They say something that's true. Looking for an Earth-like planet around a nearby star is like standing on the east coast of the United States and looking for a pinhead on the west coast with a very bright grapefruit nearby. So this gives you a couple reasons why this is very, very difficult and amazing that we can do it all. It literally is this part. It's like standing on the east coast and looking through a telescope for a pinhead on the west coast. That's hard enough. But further, you have this enormously bright star next to it. So you're looking for this very dim planet next to a really, really bright star. So it's very, very difficult. So I'm going to talk about some of the ingenious methods for detecting exoplanets. And one of the main telescopes for doing that is called Kepler. Okay, and this was NASA's first mission capable of finding Earth-sized and smaller planets. And the idea is, so it's a satellite, right? It's a telescope satellite that uses what's called the transit method. That is, it sits there looking at stars, okay, and it notices if a planet crosses the star and eclipses the light from that star. Basically, you don't see the planet directly, though. We can't resolve. We don't literally see a star with a little black dot going in front of it. Instead, we just see the brightness from the star dip a little bit. So that's what Kepler is looking for. But I'm going to go over 5 different methods. So there's 5 methods you can use to look for exoplanets. There's the transit method. That's the one I just described. That's the one that Kepler uses, and it's the most common. But you can also use radial velocity as you look for the wobble of the star due to the planet tugging on the star. Remember, stars cause planets to orbit them, but planets also pull back on stars, causing them to wobble. You can use what's called gravitational microlensing. That is, you look for the twinkling of light due to gravity actually bending light from stars. you can look directly. If the star is really close, you can actually directly image large planets. Okay. And finally, there's astrometry, which has only been used once to actually discover an exoplanet. And there, you're actually physically watching the star move, not just wobble. But you're actually watching the star move due to its orbit being influenced by exoplanets. So here's a plot showing, the fact that we use all of these methods, but by far, what happened very suddenly, what happened very suddenly around 2014 is this Kepler mission started observing transits. So while we had discovered, maybe a few hundred exoplanets, suddenly in 2014, we started discovering thousands. So this is a very recent, really it's the last decade, where we've been able to discover suddenly thousands of exoplanets and learn about all these other alien worlds. So the most recent kind of and successor to Kepler is called TESS, Transiting Exoplanet Survey Satellite. So in addition to Kepler, you'll sometimes hear about TESS, and it's kind of about to eclipse Kepler in terms of how many exoplanets we found, but it uses the same method, the transit method. And that's what I want to talk about now. So transit method is when essentially you have, say, a planet eclipsing a star. But for us, remember, when we get an eclipse, it's very special in that we have a moon in the sky that covers the whole of our sun, right? But you can have an eclipse that's not a total eclipse due to, when Venus crosses the sun. When we watch Venus cross the sun, it's just a little black dot crossing the sun, okay? But what that does is it lowers the amount of light we see from the sun. And we can do the same thing when we look at faraway stars. If you have a planet that's orbiting that star, well, say the planet orbits once a year. Well, once a year, it will actually, if its orbit is inclined sideways to you, then once a year, it will pass in front of that star and eclipse the star, causing the star's brightness to decrease a little bit. Okay? This means that if we want to use this method, we do have to get lucky, and we have to look at a solar system edge on. Okay? And if we're looking at a solar system edge on, we can see periodically, maybe once a year, maybe once a month, depending on how close this planet is to the star and how fast its orbital period is, we see this. We see the star is bright, and then brightness dips a bit, and then it goes back to normal. We see that, again, once a month or once a year, depending on the orbital velocity of that star. Of that planet. And here's some example light curves. So this is the sort of thing we see, right? So here, this is over a matter of hours. We see this planet passing in front of Kepler B. And it's they've labeled the different planets: Kepler 4b, Kepler 5b, Kepler 6b, Kepler 7b. And you see here's the light curve for Kepler 4b. It dips just a little bit. The light curve for Kepler 5b dips much more, indicating this is a larger planet, right? And so on. Okay, so here we measure the orbital period, meaning an entire year for this planet is 3.2 days, for example. And the size of the planet here is 4 Earths. So this reveals, by the way, another characteristic of this technique, which is that you're more likely to see larger planets, okay? Larger planets because they obscure more light from the stars, so they're easier to see the eclipse. But also planets that have a small orbital period, because that means they hug close to the star, and so they're more likely to cause an eclipse. So we tend to see examples, right? So all these planets that we discovered, for example, are larger than the Earth, and they also have very short orbital periods. So they're hugging very close to their parent star. And we happen to see a lot of exoplanets like that because they're the easiest to see, not because they're the most common, but they're the easiest to see. Okay, another method for discovering exoplanets that doesn't rely on getting lucky and having the planet orbiting edge on relative to our eyesight is to look for Doppler shift due to the wobble of the star caused by the gravity of the exoplanet pulling back on the star. That is, as the planet orbits the star moves towards the planet due to the planet's own gravity pulling back on the star. And so the star wobbles. And so remember, if the star is wobbling towards us, then the light from the star is what we call blue shifted. And if the star is wobbling away from us, the light is we call red shifted. And therefore we can watch the light from that star twinkle bluish reddish, with a very specific period corresponding to that planet's orbital period. And in that way, we can infer the existence of an exoplanet, and we can figure out its mass, depending on how much it's making that star wobble. So this is a rather ingenious method, and it works. But like the last method, it's more likely to be able to see planets that are large, because those only large planets, that is massive planets, are pulling on their parent star enough to cause that star to wobble so that we can see its motion through the Doppler method. Okay, another method is gravitational lensing. Okay, gravitational lensing is this amazing technique based on the fact that gravity itself bends light. So here's an example. So so the way it works is you look at some distant star. Okay, call that the source star. So you're just watching some distant star. But suppose something that you can't see very easily, like a planet that's dark, moves near that star. Well, what happens is the light from that distant star gets bent as gravity pulls the light around that star. And what that causes is the star, the light from that star that reaches our eyes is now coming from a different place. So what we see are the star appears to kind of change brightness and move around a little bit. It basically looks like it twinkles. That's called gravitational lensing. And so here's actually watching what happens when, so here's our distant source star, and there's this other solar system coming between our line of sight and that distant star. And what we see is when that star in the solar system that's passing towards us comes close, it causes the distant star to get brighter. And that's this curve here. Okay. But then additionally, you see another little blip due to the planets. Okay, so here, this is an example of a light curve from one solar system moving in front of the line of sight of a distant star, and we're watching that distant star twinkle, and we see the distant star gets brighter, starts to get less bright as the star passes, but then suddenly blips up again, gets bright again due to the exoplanet passing in front of the distant star, the source star. So you get a light curve that looks like this, and you can measure due to this thickness of this twinkle within a twinkle, you can measure the orbital period of that exoplanet. So this is another brilliant technique that actually works, that has allowed us to discover hundreds and hundreds of exoplanets. Finally, there is direct imaging. Well, not finally, I'll have one more after this technique. So there is direct imaging, though, that we've been able to do to some planets if they're close. So here's an example that's 120 light years away, close enough that we can actually directly image planets around a star. Okay, so here we blacked out the star because the star is so bright, but here we see 3 planets labeled B, C, and D orbiting around that star. Okay, and in that case, we can actually watch them orbit over time. Okay, so there's that example. Here's another direct imaging example. We see these 2 planets with the arrows pointing towards them. This one's 300 light years away. I've shown you before the disks around Beta Pictoris. So this is an example where this is like a protoplanet. This is a solar system that's in the process of forming, where we've directly imaged it. Okay, then the 5th method, called astrometry, is the fact that I mentioned that a star will wobble, right, over say months or years as it's a large planet around it pulls back on the star, causes the star itself to wobble. An example is our own sun. So our own sun we can do astrometry on, and we watch that the center of the sun actually follows this path. So there's a path. Here it's been, we've watched this where the location of the sun is wobbling from 1945, and it's followed this interesting path. And that's due to the tug of all the planets around our own sun, mostly Jupiter. Jupiter's the most massive, right? So the Jupiter is tugging back on the sun and causing the sun to wobble. We can watch it wobble. And we've done this to other solar systems, and we've discovered one planet that way, exoplanet. Okay, so that's how we discover exoplanets. Any questions so far? So this is, I've shown you a number of comics from XKCD, who's an excellent web comic who focuses on sciencey stuff. This comic was done in 2012, so it was back when exoplanet hunting was still in its infancy. So this shows all at that time 786 known exoplanets to scale. That is, in this little box is our own solar system. That is, you see the largest of these, the kind of one where I'm pointing is Jupiter as the largest planet in our solar system. And then what this shows is that most of the other exoplanets we've discovered are also very large, right? And again, that's not because most planets around other stars are large. It's because those are the ones we can detect. Okay, we have a detection bias. We can detect only really large planets. They're easiest to see. So when I show you the plots of the sort of planets we've discovered, most of them are going to be large. And that's because of this bias. Okay? And if XKCD were to update this plot, right, it would be about 10 times larger because there are just so many, which is probably why he hasn't updated the plot. Here's another nice plot, though, done by someone else. This is a portrait of all habitable zone planets. So now things have progressed since then. Not only have we detected lots of exoplanets, but we've also detected lots of planets that are in the habitable zone, meaning not too far away from the star, not too close to the star, such that they could support liquid water and therefore life. And these are all the ones that have now been discovered within just 60 light years of Earth. Okay. So if we look at, so this is using the exoplanet archive, you can go through and make plots. And one thing I've done here is I've made a plot of orbital period of the discovered exoplanet on the x-axis and size relative to Earth on the y-axis. So what you see, for example, is that most exoplanets that have been discovered from Kepler, this main telescope that was searching for exoplanets, are between Earth-sized and Neptune-sized, so between, so at least several times the size of Earth. Most of them have orbital periods much, much less than Earth's orbital period. So here's Earth. Earth has an orbital period of 365 days. Most of these exoplanets have orbital periods less than 10 days. And remember, that's because these are much easier to discover. It's easy to see planets that hug close to their parent star because then they're more likely to eclipse that star. And that's how Kepler is detecting these planets. There's another thing we can measure, though. This is cool because, right, we know all about our own solar system, and now we are beginning to be able to measure things about planets in other solar systems. One is how circular are the orbits? What is the eccentricity? So here, again, on the x-axis, I have orbital period. That is how long a year is for one of these planets. And on the y-axis is eccentricity. That is, and each eccentricity of 0 corresponds to circular orbits. So most planets, just like in our own solar system, most exoplanets have nearly circular orbits. That's what you see here. Most of them are down here. Most of them have very close to circular orbits. And here we're seeing mostly two colors. The transit discovered planets from Kepler, and also some using the radial velocity method that are shown in red. The point being that different detection methods are going to see different things, again, because they're sensitive to different things. Remember, the transit method is mostly going to see planets with a short orbital period. That's why the green are more to the left in this plot. Whereas, say, the radial velocity method doesn't care as much about the orbital period. Okay, it's mostly the radial velocity method is going to detect just really big planets because they tug more, remember, on the star. In addition to eccentricity, we can look at the mass of the planet. So here's the period again on the x-axis. That doesn't change from the last plot, but on the y-axis now I'm plotting the mass. So you see that most of these exoplanets we discover are very massive. So here, one corresponds to the mass of Jupiter. We're seeing mostly planets that are like the mass of Jupiter. We see some that are Earth massed, so which would be down. Here we also see now on the x-axis we have the separation from the planet star in astronomical units. Remember, Earth is at 1 astronomical unit. Here we see that most exoplanets discovered are very close to their parent star, which we, as I said, is because they're more easier to detect that. Okay. But we have detected some that are the same distance as the Earth. Here's the radius. So not only do we have the period, like I've shown you before on the x-axis, but now not the mass, but the period, the radius. So we see a lot of stars that are 1 here in Earth radii that are the same size of. See a lot of planets that are 1 Earth radii, same size as Earth. But again, most of them are larger. So most of them, because they tend to be more massive, and because in the transit method, they're easier to see. They block out more starlight, so we see them more easily if they're larger. Okay, so we tend to see, on average, stars that are 3 or 4 times the size of the Earth. What about Earth-like planets? So this, of course, is of great interest, right? How likely are we to see planets that could harbor life? So that's where this term comes in, habitable zone. So, right, if you're too close to your parent star, like if you're like Mercury is too close, it's going to be too hot. But if you're Jupiter, far away, you're too far. Okay, it's going to be too cold, and you're not going to be able to support liquid water. So there's a habitable zone that we identify where a planet could support liquid water on its surface, just like Earth. And we have been discovering planets inside the habitable zone. The very first one that was Earth-sized and within the habitable zone was around the red dwarf star. Now we'll talk all about in a few lectures about types of stars. There's a type of star called the red dwarf, and it's about 500 light years away. Okay, so it's given the name Kepler 186 star system. So a lot of these star systems are given the name Kepler because Kepler discovered them. The Kepler telescope discovered them. And the exoplanets are labeled with letters of the alphabet, A being the closest to the star, Z being farthest away from the star. So 186F is one of these exoplanets, A, B, C, D, E, F, so 6th away from the star. It's in the habitable zone, in other words, about Earth distance. So it could support liquid water. And we have various ways of trying to quantify just how similar an exoplanet might be to Earth. Now, why Earth-like? Well, because Earth is the only planet we know of that supports life. So if we're interested in potentially finding planets that could support life, we kind of make sense to maybe come up with an index where 0 is not Earth-like and 1 would be exactly like Earth, and rank planets by how close they are to Earth-like. And we call this the Earth Similarity Index. And the main thing, you don't have to worry about this equation, but the main things we put in, or the main things we worry about, are the size. Okay, we want something that's similar in size to the Earth. We want something similar in density to the Earth, right? Solid material, not gas. We want something with similar gravity to the Earth. And we want something with a similar Earth temperature on the surface of the Earth. Okay, that's given the highest weight. That's the most important. As you can see, like Mercury, well, Venus would be below 0.5, Mercury would be 0.6, so not very habitable. Mars is 0.7, so that gives you actually a baseline, right? Like Mars is something we've thought about, maybe it could be habitable. So that's a 0.7 on this index. And hey, we have found numerous now exoplanets that are much more similar to Earth than even Mars. So Kepler 438b, KOI 43302, for example. These are just examples, but we have found exoplanets that are, as far as we can tell, very habitable, at least relative to Mars, for example, much more habitable than Mars. And so I haven't updated this plot since 2015 because now it's just proliferated. Now it's gotten ridiculous. We just keep discovering more and more habitable zone planets. So we now have a large list of a list that's large enough now that it's not interesting to list each one of planets that are potentially habitable, similar size to Earth. Now we can't see them directly. We can't see them up close, but to the best we can tell, they have similar orbital characteristics, similar size, similar gravity, similar temperature. And something that's only happened in the last couple of years is people have developed the ability to actually tell if there's water on an exoplanet. So this is for the first time in 2019. Here I have the abstract of the paper on exoplanet K2-18b. They detected water vapor. And the way they do that is they watch the sunlight from that star pass through the atmosphere of that planet and detect, using spectral analysis, whether H2O shows up in that spectrum. So here, reading from the paper, so here we report the detection of water vapor and the likely presence of liquid water clouds in the atmosphere of the 8.6 Earth mass habitable zone planet K2-18b. It has a 33-day orbit around a cool M3 dwarf. It receives virtually the same amount of total radiation from its host star as the Earth, making it a good candidate to host liquid water clouds. In this study, we observed 8 transits using the Hubble Space Telescope in order to achieve the necessary sensitivity to detect water vapor. So this is really exciting. Okay, so we actually know of habitable zone Earth-like planets. This one happens to be much larger than Earth, but we know of habitable zone planets that have liquid water around other stars. This is rather cool. And here's just a histogram of the nearest confirmed exoplanet. So that is, if we go outward from the Earth in light years, right? The nearest star Alpha Centauri, is 4 light years away, right? So we go to the nearest star, we already find an exoplanet. Okay, and I've indicated that in light blue are ones that are potentially in the habitable zone. So even right, so we're seeing as we go outward more and more, first of all, stars shown in these light gray lines, because the further out we go, the more and more stars there are. Okay, and then around those stars we look for exoplanets, and even within, just 20-30 light years, there are dozens. Here, I'll give you a poll question for participation. Okay, so based on what we just talked about, how close is the nearest exoplanet? Okay, the nearest exoplanet.
Four. Four light years. 4 light years.
Maybe 5 more seconds. And yes, most people got it right. So, I mean, this is just
Light
mostly just to make sure you're paying attention, right? 4 light years is the nearest star to us. As of course, the nearest possible exoplanet we've also discovered happens to be around the nearest star, which is 4 light years, as we showed here in this last block. Okay. So we'll talk in a little bit about, the possibility of space travel, but keep in mind that as cool as this is, and this is very cool, even getting to the nearest star, which is 4 light years away, is not easy. It's something that would probably take multiple lifetimes, right? If you were to travel and attempt to do it. And it's still the sort of thing we're developing technologies, maybe to be able to send unmanned probes, but still it's the sort of thing that we would probably have to wait around a lifetime before we started seeing pictures from such a mission. Okay, so are there any questions so far about exoplanets? So one really cool thing about the study of other solar systems, which we can now do just in the last couple of decades, is we can revisit our understanding of nebular theory. That is the theory of how our own solar system formed. Why? Because we can see. We don't just have a data point of one, we can see hundreds, even thousands of other solar systems and what their characteristics are. So remember, nebular theory was this theory originated in the 18th century, that our solar system formed from a giant cloud. In other words, a nebula. Nebula is a name for cloud of interstellar gas and dust. Okay. The idea was you have this large cloud of gas and dust, and under gravity, the denser regions contract, right? And they undergo a process of heating, spinning, and flattening. That is, as you contract, that gravitational potential energy has to go somewhere. It goes into heat, so it gets hot. Okay. Angular momentum is conserved, so like a figure skater pulling in her arms, it starts to spin faster. And then finally it flattens because you have particles initially going in all directions, but they knock into each other. They knock each other out of the way until they're all going in the same single direction. And remember, that explained a lot of features of the solar system. For example, as the solar system cooled, you have compositional differences due to the frost line. You have the fact that everything's spinning in the same direction, that everything is more or less in the ecliptic plane. Okay. Right. So remember, we talked about the frost line and how after this disk of debris cooled down, after the frost line, the ice could condense. But before that, ice couldn't condense. So before the frost line, you get the terrestrial planets, right? After the frost line, you get these big balls of ice that could then collect the remaining hydrogen and helium from the solar nebula and became these gas giants. Right? Furthermore, it explains why there's comets in the outer solar system, but asteroids in the inner solar system, right? But one thing we've discovered, so one of the new discoveries from all of these exoplanets we've discovered is that we keep discovering these really, really big Jupiter-like planets that are close to their stars. Now, in one sense, remember, this is expected because we have this bias. That is, these planets might not be very common, but they're the ones we see most easily because, one, we see large planets more easily. And two, we see planets that are close to their host star more easily. So we're most likely to be able to see, if they exist, these so-called hot Jupiters. That is a Jupiter-like exoplanet that's close to the star inside the frost line. So this is one of the main things that we've observed that's in tension with our nebular theory. Okay, the fact that we do see so-called hot Jupiters, or Jupiters that are close to their parent planets. Right, so one of the surprises is that some of these massive planets orbit very close to their hot stars. Those are called hot Jupiters. We've also discovered that some extrasolar planets have highly elliptical orbits, which is, now again, most of them don't though. So generally, by and large, nebular theory holds up really well, but these are the two surprises, right? We see a little bit more planets that are in elliptical orbits than we expect, and we see more hot Jupiters than we expect. So this has forced a re-examination of nebula theory, and this is good. This is what science does. We read data and we learn from it. And so one of the modifications to nebular theory is that we now know that it's more common for what we call planetary migration to happen. That is, planets don't just stay where they started out, they can actually move through interacting. They can interact gravitationally and kind of slingshot around more than we thought. And this is confirmed when we do simulations. In other words, we now understand that you can have, this is called the Nice model, after Nice, France, that we think that these large Jovian planets, they did form outside the frost line, but they did move around a bit. They got kind of slingshotted around, and part of what that caused was the late heavy bombardment. That is, so we have this theory where we have the terrestrial planets inside the frost line. Then past the frost line, we have the large Jovian planets formed. But then we have a theory of how, right, remember this was a complicated time. There was lots of stuff interacting gravitationally. And those interactions tended to cause these Jovian planets to fall inward towards the inner planets. And then over the next 100 million years or so, they interact some more and kind of whip themselves back out. And when they do that, they created the late heavy bombardment, because as these large planets are moving outward, they are slingshotting all this debris both towards and away from the inner planets. So that one creates an uptick of asteroid impacts, and two creates a bunch of debris in the outer solar system that's part of the Oort cloud. And remember, right, we talked about the late heavy bombardment as being the fact that, so if you just look at this black curve here, this is what we expect, and this is what we mostly see. That is, asteroid impacts were way more common early on in the solar system. So they're most common right when it formed, about 4.5 billion years ago. And then since then, it's been decreasing and decreasing. Why? Because every time there's an asteroid impact, that's one fewer asteroid to impact in the future, right? So you're kind of cleaning up all the debris in the solar system as there are asteroid impacts. But there was a big spike that we discovered where it seems like there's an excess of impacts about a little less than 4 billion years ago. And we call that the late heavy bombardment. And it seems that that was likely based on this exoplanet data we've seen. It seems like that's probably the result of our Jovian planets passing towards the outer part of our solar system and flinging with them all sorts of debris from what we call now the asteroid belt. And that debris got flung into all different directions and parts of the solar system. And so this explains the late heavy bombardment. Back here. This explains the late heavy bombardment. It explains the formation of the Oort cloud, that large cloud of just random debris. It explains the Trojans. Remember, there are that part of the asteroid belt are actual bunch of asteroids that are in the orbit of Jupiter. So it carried with those with it. So now we have asteroids in Jupiter's own orbit that it carried with itself from that time. And it also explains a whole lot of orbits of objects that have passed Neptune that would have been produced when they were flung into the outer solar system. And that, I think, completes what I wanted to say about exoplanets. So I can let you go a little early today. Are there any questions? All right. Everyone have a good weekend, and I will see you next week. Thank you, Joseph.
Thank you.
Thank you. Professor, I have a question.
Yeah.
Are we gonna have any homework over spring break?
That's a good question. I actually, so it's all, I have it all planned out in the calendar, but
Yeah.
I actually don't remember whether I put the homework in that calendar or not. So I guess I'll check myself to make sure what I had planned out before the course, put in the Mastering Astronomy calendar, which has all your homework listed, so you can go there and check right now.
Okay, I'll go check now then.
And I'll check it too, but I'm not 100% certain, so I'm not going to say anything.
Okay, sounds good. Thank you so much.
Go ahead. All right. Bye.